Hey guys, this is going to be 10-2 special right triangles. This particular lesson is probably going to be either really difficult or really easy. What I have on the screen is what's called special right triangles, and there's two of them. There's a 45-45-90 and then there's a 30-60-90. This is one of those kind of tricks that you can use when you're taking, say, the SAT or the ACT. Most of y'all either just recently took or will be taking the PSAT, and these are things that actually can be very helpful to answer the questions pretty quickly. Since they're right triangles, you could actually just use the Pythagorean theorem to find the missing sides, but sometimes they'll only give you one side length, and so in that case, using the properties of special right triangles can help you find whatever side you're looking for. What you see here is basically a general format that you can use. We could call it a formula. It's not really a formula, but this is like the general process that you would use when you're solving these problems. So notice that I have a 45-45-90 triangle, and then I have a 30-60-90 triangle. The 45-45-90 triangle is actually half of a square. And so if you were to try to find the length of the diagonal of a square, you would end up getting the length of the diagonal being the side length of the square times the square root of 2. And then the 30-60-90 is actually half of a rectangle. And what I mean by half of is you draw one of the diagonals and split it into two equal triangles, and that triangle that you see is that half. The 30-60-90 has side lengths x squared root 3, and 2x, where 2x is always the hypotenuse. Over here, x squared root 2 is always the hypotenuse. Sometimes it can get a little confusing because in the example they may call one of the side lengths x. That x is not the same x that you see on this page. This page is the general format that you use as like a formula, basically. Sometimes the x might be labeled as your hypotenuse, and if you had x, the actual x of the triangle side length being, say, 4, then the hypotenuse is going to be 2 times 4, so that would be 8. Now I'm going to do a lot of examples so you can see different situations that can happen, and then at the very end I'll do just some quick square root practice to help you in case you need that. So our first example here is the most basic, easiest format for this. You see here that we have a 45-45-90 triangle, and that's known, or it's understood that it's 45 because you have a 90 and you have a 45 degree angle. So automatically that makes a top angle 45. So in this case, what I like to do is actually write out my x, and x square root 2. That'll help me know what's what. Now what you see here is that the side length that is supposed to be x in the general format is the length of 5. So that means in this case that x equals 5. So if x equals 5, then what that actually means is my a is x square root 2, x is 5, so I plug in 5 for x, and that's my answer. It's that simple. Now, of course, not always will they be nice with the numbers, but if this is what they give you, your answer is 5 square root 2. So instead of doing the Pythagorean theorem here, you can actually just use this format. So example 2, this time they gave us the hypotenuse, and that hypotenuse was 6.2 square root 2. So I'm going to go ahead and label everything. Since the hypotenuse was 6 square root 2, then what I can do, and this will be helpful in the future, is set that equal to x square root 2. I can divide both sides by square root 2. Those cancel, so x is 6.2, and that is my length of b. Okay. Next example that I have here is a 45-45-90 triangle, but the hypotenuse, which is x square root 2, is a whole number, and I don't have a square root in it. So I'm going to have to do a little bit of algebra here. Now what's nice about what I'm going to do is the way that you do this on this problem is the same way you do it every time you get a whole number as the hypotenuse. So like I did on the last problem, we know that 10 is equal to x square root 2. So in this case, if I want to solve for x, I divide both sides by square root 2. And so I end up getting 10 over square root of 2 is equal to x. The problem with that is that you cannot have a square root in the denominator. So we need to multiply by 1. Now the square root of 2 over the square root of 2 is equal to 1. And we want to do that because the square root of 2 times the square root of 2 is the square root of 4, which equals 2. So the square root of 2, times the square root of 2 equals the square root of 4. You just multiply these numbers, and the square root of 4 is 2. So what happens in this problem is on the top, you just get, and I'm going to come over here, 10 square root 2, and the bottom just becomes 2. And then you reduce that. 10 over 2 is 5 square root 2. So my C in this case is 5 square root 2. Example 4, same concept, same process here. We have, this time, the side lengths are congruent, so that's what tells us that this is a 45, 45, 90. This is x square root 2, this is x, and then this guy's x. So we know that 2 square root 3 is equal to x square root 2. So we're going to follow the same exact process that I did on the last problem. So 2 square root 3 over the square root of 2. We're going to multiply both sides on the top and the bottom by the square root of 2 over the square root of 2. And that gives us 2 times the square root of 3 times the square root of 2, and we'll fix that in a second, over 2. These cancel, and these guys, just like I did up here, equal the square root of 6. When you multiply square roots, you just multiply the numbers that are underneath. So D is the square root of 6. Next example, this time I have a side length that I'm given. This is a 45, 45, 90 because the sides are congruent, and I'm trying to find the hypotenuse. So I know that x is 5 square root 2, and the hypotenuse is x square root 2. So I'm going to plug this in for x. So this is 5 square root 2 times the square root of 2. Notice here that this was my x. And then I had to add square root 2 because it was the hypotenuse. The square root of 2 times the square root of 2 is 2, so this is 5 times 2, which is 10. So there's a couple examples of the 45, 45, 90. Every problem that you will get will look pretty much similar to the ones that I just did. So if you get caught up on one, maybe come back and look at the video if you need. You can also, I would suggest copying all these down so you have them to look at as well. But like I said, these things are going to be either you get them or you don't. But it's possible for everyone to understand it. So you just got to work at it, you got to practice it. The more you do, the better it's going to be. Next example I have is a 30, 60, 90 triangle, and I know it's 30, 60, 90 because I have a 90-degree angle and a 60-degree angle. So that automatically makes this 30. Now this is x, opposite 90 was 2x, and opposite 60 was x square root 3. Well, my x is 5, so that makes this side 10, and this side 5 square root 3. Next one, another 30, 60, 90 triangle. We have the hypotenuse, which is 2x. We're looking for x, and we're looking for x square root 3. Well, since the hypotenuse is 24, I can set that equal to 2x, divide both sides by 2, and I get 12. So that means that this is 12, and this is 12 square root 3. That should be 3, not a 5. Okay, now next one. This is a 30, 60, 90 triangle, so that makes this x square root 3, this is x, and this is 2x. This time we have this situation, so we're going to have to do pretty much the same thing that we did on the 45, 45, 90 triangle, but what's going to be a little bit different here is we're going to end up having to multiply by the square root of 3 instead. So we need to multiply by the denominator over itself. Now mathematically what you're actually doing right here is you're multiplying by 1, because the square root of 3 over the square root of 3 reduces to 1. But we chose that, or I chose that, because I know on the denominator that's just going to be 3. And that gets rid of my square root. The top, 16 square root 3. If the 16 and the 3 would reduce, I would reduce it, but it can't. So this is my x, which is my d. So this is 16 square root 3 over 3. And then to multiply that by 2, all I have to do is multiply the 16 by 2. 16 times 2 is 32. So this is 32 square root 3 over 3. And then if you can reduce the 32 and the 3, that's fine. If not, you would just leave it. Okay, I'm going to do really quickly, just as a reminder, when you're multiplying square roots, like this, for example, this would actually end up be the square root of 6 times 5, which is the square root of 30. So when you multiply square roots, you just multiply the numbers that are underneath. When you are reducing when you have a fraction, say like this, for example, let's try that again, that's actually just going to stay the square root of 6 over 3. Nothing can be done to that. But let's say you had like the square root of 20 over, say 2. Well, this one can reduce because 20, if we did the factor tree, is 2 and 10, 2 and 5, and we have a pair of 2's. So the square root of 20, I'm going to move over here, is 2 square root 5 over 2, and the 2's can reduce. So square roots are a little tricky, but they are consistently the same, if that makes sense. So the more you practice, the more it'll be, the better it'll help you. You'll have to do a lot with square roots next year in Algebra 2 as well, so you'll see them again. Remember that math just builds on itself. So if you have any questions, if you need some assistance, some practice, just come see me and I'll be available to assist you. Have a great evening and I'll see you guys soon.